Well, playing in the background, we've had this view of the fireboat. I guess that's Brooklyn Bridge in the background, so we know, it looks like Brooklyn Bridge in the background anyway, so we know exactly where that is. So what we've been talking about is the first of our three journeys into talking about conservation of quantities. Conservation of mass is what we're talking about now. We'll also talk about momentum and energy in the future. We talked about relative coordinate systems because those seemed important for us to be able to evaluate conservation, not so much for static and non-deforming control volumes, but as we'll talk about today, when we talk about control volumes that might move, like a jet engine, for instance, or might move and deform, like a balloon flipping around in the room, then we need to know something about relative velocities. And so that's something that is related directly to this this video going on of the fireboat in the harbor at New York. And so where we are with this, okay, let's just recap exactly where we were last time. So where we are with this is that we talked about this theorem, Reynolds transport theorem, that allows us to say something about conservation of mass or conservation of energy or momentum. In our particular case for conservation of mass, this quantity B is equal to mass divided by mass. And so when we put it in here, this ends up being 1 and this ends up being 1. Overall conservation of the system is 0, so this left-hand side is always equal to 0. And if we do that, then this somewhat complicated expression migrates to being a slightly less complicated expression if we view it like this, and an even less complicated expression if we view it like this. Before, we talked about the idea that this was the velocity that fluid is coming out of the control volume. We called it V, lowercase v, I guess, or uppercase v as a vector. But today we'll make the case that this velocity should not actually be the velocity of the absolute velocity of flow, but it should be the relative velocity of flow relative to the control volume. And so W in this is relative velocity. And so we'll deal with that in due course. And if we want to write this out in an even less complicated way, then the way that we talked about the final form of this we talked about last time was by splitting up this density and volume part into a component that is constant density but a changing volume, constant volume but a changing density, and a sum of mass flow rates. And so in verbal terms or in descriptive terms, mass out minus mass in plus rate of change of density in a fixed volume and rate of change of volume at a fixed density gives zero net accumulation. They will have to balance. And so really this is mass out minus mass in. Mass rate out, I guess, so let's put a dot above this. Mass rate out versus mass rate in. Remember the sign convention we talked about was positive for mass out and negative for mass in because of the dot product that occurs here. And rates of change of volume are positive if the volume increases, and rates of change of density are positive if the density increases with time. And so we're just summing rates, and we can use that to be able to say something about the system. Okay? So let's apply this then to some simple systems. We've looked at this before, but let's turn it down again. Okay. So you see that to the right. So one of the simplest systems we could look at is filling up a bucket of water or a glass, a beaker. And so no particular magic here in terms of how we might apply this. I think we could all calculate, if we know the rate of which fluid's going into that, how quickly it would take to fill up, just by looking at the mass rate and dividing the total mass of fluid in there by the rate at which it fills. And that would give the time it takes to fill up. So there's no particular mystique in that. So what we can do, though, we could use this to be able to make the case that we can say something about it based on our understanding of control volumes. And so before we turn the faucet on, so right at this segment here, so if I wind it back and make the water go uphill, so if we start at that point, just as we're getting this first drip of water into the system, it's not very difficult for us to be able to calculate the rate at which it would flow. And let's just do that calculation as a preamble to what we'll talk about today. And so we have this beaker. We'll idealize it as having a cross-sectional area A on the bottom. I guess I could draw it in perspective for this one. It has some height, which we'll call lowercase h, and it has coming into it a jet of water, which starts right at the top, and that jet of water has some other cross-sectional area, and it has some velocity, which we'll call v1. And so from this we know that the total volume of this has to be equal to the height times its area, just by looking at the geometric shape. And if we want to calculate the time it takes to fill it, then what's that? We could get that from just dividing the mass rate divided by the total mass, or the volumetric rate divided by the total volume. We tend to use masses because we conserve mass. It's a much more useful quantity to conserve because it's mass that is constant. For instance, if you blow up a balloon and then you heat it up, then the balloon gets bigger, but the mass stays constant, the volume doesn't stay constant. And so typically we conserve on mass because it's a more fundamental quantity to work with. So what is the mass rate in this? The mass rate is the cross-sectional area of the flow into it, its velocity, and its density, quite simply. And the mass is just the volume multiplied by the density. And so if we look at this and we look at this magnitude here, okay, is that right, I guess? Thank you. So 1 over time. Thank you. This is mass rate, so mass divided by time divided by mass is 1 over time, so it's the reciprocal of that. And so in other words, this ultimately we can take this out, and we have the ratio of these two. This, by definition, is what we would term a volumetric flow rate. And so if we look at changing this to the correct notation, the time to fill will just be 1 over this. So it's equal to the volume divided by the volume rate. Yeah. My apologies. So this is, we could have done that. You don't need fluid mechanics to be able to do that calculation. So what we're going to do today is we're going to talk about each of these ways of conserving mass, and we'll use this very simple analog of the filling beaker to do that. But the analog we need to use is slightly different. And so what we'll do is, again, we'll talk about this same velocity coming in. Then we'll talk about this same height, h. We'll talk about this same area. and we'll talk about this this subsidiary area, A2 we'll call it, and we'll say that the total area is just equal to the sum of these two areas. So area 2 is the one that I'm going to shade in. So it's everything but this other portion. So area total is A1 plus A2. Okay? And so what we're going to do now is, instead of just repeating the calculation we did here, we're going to let this jet come down to the bottom, and that is going to be our time t0. Okay? So in other words, in this, I'm going to start this with, if I can move it, so this, am I able to do it with this? I missed it. So in other words, just when it hits the bottom is going to be the time that we deal with here. And so to be able to do this, we can do two calculations. One is the time for the column to come to the bottom. What's that going to be? It's going to be equal to, let's do it right this time, it's going to be mass divided by mass rate. The mass of this column in here is going to be area 1 times the height times the density, hopefully. The mass rate at which it's flowing in is going to be the same as before, which is going to be the density multiplied by area 1 V1. Okay? So that's the time it takes for the drop to come out of the faucet at the level of the top of the glass and hit the bottom. Ignore the issues of the fact that it's accelerating and getting thinner as it goes down. We don't want to deal with that. And so on top of that, let's then talk about how long it takes to fill up the, I was going to say the bucket, but it's not a bucket, tea glass. Well, again, it's going to be the mass divided by the mass rate. This is going to be the mass rate of the column, and this is going to be the mass of the glass. So what's the mass in the glass? Well, the mass in the glass is going to be the area 2 multiplied by the height times density, right? So this shaded area here, everything but this column that's come here is the remaining volume that has to be filled. And the mass rate is going to be no different from the previous one. It's going to be exactly the same, right? Because we're filling it at the same rate. So this is A1 V1 times rho. Get rid of these in both cases, so we don't care about those. And if we look at the total time taken to fill, it's equal to TC plus TB, or TG rather, T glass. And if you look at these individual components, we see that the denominator is the same in both cases, it's just A1 V1. But the numerator has the same multiplier, but it's equal to the sum of these two components. So A1 plus A2. And of course, A1 plus A2 is the same as being A, because of our definition here. And so, obviously they're equivalent because it's the same behavior. But what we've done is we split it into two parts. And the reason for doing that is that if we want to look at these behaviors of a static control volume and a moving control volume that doesn't deform and a moving one that does deform, it's easier for us to start the case in looking at this behavior here, in which case all of the solutions should be the same. So in other words, we're going to start time 0 at when the water hits the bottom of the glass, and we'll go through it. And so it follows from this that, not obviously, this is the part that is due to filling the glass, or sorry, getting the bead down from the lip to the bottom, and this is the part that is due to filling up the rest of the glass, which is just the volume remaining in the glass after you do that. Okay? So that's what we're going to attempt to do. And so that is the first bit of understanding. Okay? So what we should find is in our calculations that all of our calculations should turn out to give us T glass is equal to A2H over Q. And it's the glass minus the column, right? So it's this one. So let's look at this. So this is the behaviors that we're looking at. So similar to the fireboat, we can look at these three cases in case. A non-deforming body that's not moving. And so we can define a couple of things. We can define a control volume, where we've talked about the volume. So obviously if this is some container, happens to be a ship shape in this particular case, if the control volume is remaining constant, it's not expanding or contracting, and if it's physically static, it's anchored, then we can use exactly the expression that we've used before to do this. This is our expression that we had before, and that we wrote somewhat more straightforwardly here, is we wrote it as this. So this is exactly the expression we can use in that particular case. And that's the first example that we've done. And so if we wanted to apply that to our particular case, then this is the first case to look at. And so let's just walk through it. So we're taking this glass with the bead hitting the bottom. So the bead is hitting the bottom as it starts. We're going to define a control volume, which is here. And as a function of time, this water level is actually going to rise. I'm going to take those off, but that's what's going to happen. And so in this particular case, it's a little more complicated than before, but it's convenient for us, again, to divide it into an area for this bead and an area that's the rest of it. But let's just think of it in terms of this kind of schematic where we have, this is the area of the jet that's coming down, A1, which it was before, and this is the area of the jet which is where there's nothing there, but it's filling up. And if you like, what we're physically going to do, and I guess we have a picture of this, is, sorry, there is one here, I'll be back here, is we're going to take this figure, I can't draw on the video, but we're going to take a control volume that basically looks like this. It's pretty light on here, but it's this bottom part. And so clearly there's a jet going into this control volume, and there's a surface that's rising up from this control volume. But we're going to keep this at a steady, non-deforming control volume. It's this red brick, this red rectangle, which is really a hockey puck, right? Which doesn't change in size as the water fills up past it. And so that's the geometry that we're trying to accommodate here. And so let's try and apply our expression. This is our Reynolds transport theorem. These are the rate change terms. These are the mass in, mass out terms, which you've just written out. We've written these things in the right sign convention. V1 is into the control volume, and so it is negative. The scalar value of this is negative. And V2 is out of this, right? So we're keeping this volume straight, but this surface is slowly rising with time. So the surface has some velocity that's coming out of it. And so let's look at these individual terms. The rate of change with volume with time. Well, the control volume is set here, and clearly isn't changing volume with time. So this, by definition, has to be 0. The density is not experiencing any big change in pressure. That's the only way that we can change the density, because it's just atmospheric pressure it's feeling. It's perhaps got a little bit more pressure at the bottom than it does at the surface, but it's negligible. And so this, for a liquid, just like density change, just like for a gas, well, actually, it's not a good analog. For a gas, we talked about the unit weight being inconsequential. In a liquid, the density changes due to small pressure changes are inconsequential. So this is 0. We have, going into this control volume, a jet of water, which is going at velocity v1. It has a cross-sectional area. So this magnitude here is a volumetric flow rate. If we multiply the volumetric flow rate by a density, we have a mass flow rate. And in our sign convention, because it's physically going into the system, it's negative. And so we don't have to deal with dot products because it's orthogonal to the surface. So that's the one that's going in. If we look at the surface which is rising out of here, it's rising up at some velocity v2. It covers an area which is this area here, a2. And so this is q out of this area a2. This is q out of this area a1, not multiplied by, just, if you like, a subscript. And again, this is a density, so this is the mass flow rate here on surface number 2, and this is surface number 1. This is out of the control volume, so by our sign convention, this is positive. This is into the control volume, by our sign convention, it's negative. And so the only two components we have to equate with each other are these, and if we get rid of the densities, which don't change, then we end up with V2 being this. And if we wanted to, we could do exactly the same as before. The time to fill is the volume divided by the flow rate, which is the same as the mass divided by the mass flow rate. And so if we do that, then we end up with this final expression. This is Q on the bottom, and this is the remaining cross-sectional area once the bead has hit the bottom of the glass, multiplied by the height of the glass. So it makes sense. So it's the calculation we've done before. So that's a bit more of a formal way of doing it, but it's basically the same calculation we did already. Okay. So let's, for kicks, try and make things tougher. We won't do this question, but we'll do the same example. So now let's take the case of the moving fire launch. So now we have to make an extra definition. So the second case is a moving control volume, but one that isn't changing with time. So the jet engine. So the boat is now moving, but it's not changing its size. It's not being contracted, so I'm not sure. And so now we need to make the case, and it's probably easier to do it for this. And let's just do it for the jet that is squirting forward at velocity w. And so w, we'll define w as being the velocity of the plume relative to the observer on the control volume, right? So you're standing on the ship, you're pumping water out at 1 meter a second, and you're going from left to right. If we choose our x, y, and I guess z is out of the page coordinate system, this vector w would be equal to what? It would be equal to 1 in the x direction, 0 in y, and 0 in z, meters per second. If the ship, the control volume, is moving at 1 meter a second, actually let's have it 2 meters a second, just to differentiate, then the velocity of the control volume and the control surface, since it's not deforming, is then going at, well, you know this, 2, 0, 0. And so relative to the guy or the gal who's standing on the quayside watching this, the relative velocity, or the true velocity of flow relative to that observer, is equal to the sum of these two components. So in other words, this velocity here is equal to the squirting velocity out of the ship plus how fast the ship is going. So in our case, if we do the vector sum, then it's 1, 0, 0 plus 2, 0, 0 is equal to 3, 0, whoops, 0, 0. So that's it. That's all it is. And so all we're saying that when we accommodate for the conservation equation, we have to accommodate relative to the control volume. And so the velocity that's of interest to us that we conserve, the mass flow rate, is going to be the relative velocity that it crosses outside the boat. Not the absolute velocity relative to the static observer, but the relative velocity that it's coming out of the boat. And of course, that makes perfect sense, right? If we're squirting things out of the front of the boat at 1 meter a second, and we know the area of that, then the flow rate would be equal to 1 meter a second times the area of the flow. Just common sense. And so that's really what this is going to be used for. So that's the only kind of mental gymnastics we have to do. And if we do that, then this relative velocity goes into the mass rate out minus mass rate in term. This has to be relative. Okay? And so this is what we need to remember. You need to remember that the static observer velocity has to equal relative to the ship plus the speed of the ship. That's it. So ship speed, it's a vector, but we'll just use it as a scalar. Out of ship, and this is static observer. So that's why we spent some time. That's why we spent some time talking about material derivatives, substantial derivatives. It matters what our frame of reference is. If we're in the elevator, then we can look at accelerations from an impartial location, and we can convert between the acceleration you feel on the elevator, uppercase dv dt, versus the acceleration you see as velocity changes in space as a static observer. So it's analogous to that. Yes?
I'm sorry, what is the word that's with the W equals velocity?
Out of ship.
Oh, no, up here. Like
This one?
Stick figure.
Stick figure? Where? Relative?
Yeah, the word before relative.
Velocity of plume. Plume. Yeah, sorry. Yeah. Well, yeah. My handwriting. Okay. So let's do an example with this moving control volume, but not stationary. So we'll zip back to our figure. Whoops, wrong figure. Wrong figure 2. It's this one, I guess. And so now, hopefully I can erase this. So now the control volume we're going to take starts off here. If you can see that, it's kind of light. It's a hockey puck at the bottom. And then at some time t, it's up here. So the hockey puck basically migrates. And we're going to let it migrate with this upper surface here attached to the top surface of the water. Right? And so it's a non-deforming control volume. It doesn't change in volume, but it physically migrates. And so that's the geometry we're going to choose. So let's look at doing the calculation again. So on this figure, it starts off here, and it migrates up here to this dotted location. I suppose the one thing for us to keep in mind is that this top here is always the surface of the water. That's the key issue. CS stands for control surface, which is the boundary of a control volume. So, control surface. And so let's do our calculations again. For the same arguments as before, this is now our conservation equation. The control volume is not changing with time. It's a hockey puck which is migrating, but the bottom of it is traveling as fast as the top, so the volume doesn't change. The density of water doesn't change because there's no pressure change, so we can get rid of this term. And all we have to then do is an accounting of the velocities as we move this hockey puck up. So this is the hockey puck. This is the surface on the top, which is always equal to this whole volume, if you like, is moving up at some velocity v2. There's fluid coming in here at velocity v1. This has area a1, and this has area a2. So the total of these is just as before. Remember, we have to talk in terms of relative velocities. So the car collision, That's not a very good analog to you. Let's not talk about car collisions. So this fluid is coming in here at V1, but this whole surface is moving up at some velocity. And so if we want to look at this, then the relative velocity here, I guess, is going to be, we'll call W1. So let's do the accounting. So location A is this point, no, wrong term. Location A, lowercase a, is this point here. And so this is this one. Density of water, cross-sectional area, times the relative velocity. We'll figure out what the relative velocity is. Presumably, velocity is going in here, and the surface is going up, so this has to be a negative, right? Because this net flow has to be net flow in. We're going to look at this surface here. We said this surface is attached to the top of the hockey puck. So the density of fluid multiplied by the relative velocity here multiplied by the area of just this portion. We've said that, so we can get this if we know the relative velocity, the area, and the density. We need to know the relative velocity of this surface relative to the water. We've said we've pegged it to the top of the fluid surface, and so by definition, this has to be 0. We don't know whether it's plus or minus, but it doesn't matter in this particular case because it's 0. Right? There's no net magnitude. It doesn't matter if it's 0, obviously. And finally, the bottom of the hockey puck is moving up. And it's moving up at the same velocity all the way across here as the hockey puck is moving up. And so the density of the water, so that's 2. So this is the relative flow rate. This is Q. And I guess I didn't label this as B, and I didn't label this as C, but this would be B, obviously. And this would be C. So this is the relative velocity and the density. And so what is the relative velocity of this flow relative to this? Well, we know that this whole thing is moving up at velocity V2. We know that the fluid is just sitting in here in the bottom of the beaker, it's not moving. And so relative to that control surface, the control surface as it moves up at velocity V2 in a static fluid, if you attach yourself to that control surface, you see water flowing out of that control surface as velocity V2 going out, and out is positive. And so this is positive. This is equal to, in this case, this is actually equal to W, relative velocity, and the area and the density. And so you can go through these calculations here, but that's the best explanation of it. So if we look at taking this expression here and defining exactly what these components are, then we end up with this. So this has to be equal to, yeah, do we have 3 components? We have this component here. We have this component, I guess I haven't done that necessarily with these. We have this component here, which is the relative velocity on the surface, which is A2. And we have the basal part, which is equal to this part here. And so, why aren't I getting this? So if we take this, what do we have as our unknown in this particular case? We have this magnitude, which we don't know is V2, I guess. We don't know what this is. We have to equate that. So if we try equating this upper expression, we have rho A V2, which is this term here. I guess this is C. We have the term that we have here, which is a velocity coming in plus a control surface going up at velocity V2. And so this term here has to be V1 plus V2. And so the only terms we have are this term for this surface A, the full bottom of this. If we equate them, then this is just A. Okay. If we equate them, we get this. This is the rate at which the top surface goes up. If we take the time it takes to fill as the mass divided by the mass rate, then it's the same as the height divided by the velocity. We could just multiply these by, if you like, area 2 and area 2, if you like. And if we have these, mass flow rates in. So in other words, what is this? This is the area times the height. So this is the total volume, which is A2 times H top. The mass rate in is not A2, is it? It's A1 times. It's actually, let's take this out. It's A1 V1, right? Mass rate in is density times A1 V1. Mass rate total is the height times area 2 times the density. And if you rearrange this equation, you end up with exactly the same expression that we had before. This is the time it takes to fill. So this is the volume, neglecting the bead until it hits the bottom. And this is the rate at which it fills. So this is just volume flow rate divided by total volume of what we call the glass volume. And so we should have exactly the same result as before, because it's the same exact problem, but we've chosen a different control volume to be able to get it. A2H times V over V1A1. Gone too far. Okay. So A2H over A1V1. So exactly the same expressions we had before. So no different. And of course it shouldn't be, because it's the same physical problem. Yeah, go ahead.
Why are we able to set W2 equals 0 again?
Because the top of the hockey puck, control volume, follows this surface, and we're just choosing that it follows this surface as it rises. So the surface rises, the puck's attached to it, so there's nothing going across that surface. Yes? This one here? My bad writing here, yes. Volume of the glass divided by Q. So in the very first thing we talked about the volume of the column, we talked about the volume of the glass, excluding the column. Yeah. All right, so it's kind of mind-blowing, isn't it? Kind of a little, taking a relatively simple problem and make it progressively more complicated. So we can also do the same for a deforming control volume. So this is the case where not only is fluid coming out of the ship, as it was before, but the ship is changing in volume. So it's the balloon floating around in the room as you just release the pressure on the balloon. And so we can do the same thing again. It ends up being the same expression we had before. This is 0 as we had before. These are the rate of changes of the volumes and the density on the left-hand side. And so now the mass balance across the control surface is the same thing, except now you notice that the integration, different from last time, if we skip back, very subtle difference, is, I guess it's the same. This is the control surface. In the case where the control surface, the volume isn't deforming, this is also the surface of the control volume. Right? In other words, the volume isn't changing, and so this has to be the same as the control volume. It's static. But in this case, we have the control surface, which might be changing independently of the control volume. And so we have to be able to accommodate for that in this change across the surface. And actually the accounting we did was really an accounting on the control surface in the last time. So let's see if we can figure out how to do this. I'm not sure which, let me just look quickly to see which is the more straightforward one. I guess this is the one we Yeah, let's try this one. Yeah, let's do this one and see if we can work it out. Yep, go ahead.
When you say deform, what exactly do you
I mean the ship is getting bigger or smaller. So it's going across in front of you, squirting fluid out, but it's also getting bigger or smaller. Just like the balloon that we let go in the room, it squeezes air out of the back of it and it flits around. So it means the control volume is changing. Yeah, go ahead. The previous example, this one, the volume is getting larger.
So how is it moving?
Sorry?
How is it moving?
We can do it moving at the same time if you want. It's moving because you have to choose what your reference frame is. So yeah, you see exactly what's going on, right? So this is the volume that it starts with. This is our control volume. So that's a good point. Then the volume that we take expands to be this one. And so what was the smaller volume expands to be the larger volume. So if you attach yourself here and you think that's your reference frame, then the volume isn't moving. But you've arbitrarily chosen that part of the surface. If you attach yourself to this part of the surface, then it is moving. Yeah. So it's all relative, right? I think we'd all say that this isn't really moving because it's attached to the bottom, but actually it is. Right? I suppose by definition, you could say that it's not moving if any part of the control surface is fixed in space. So by that definition, it's not moving. So, if we go back to the other one, is this moving? Yeah, the same. So let's talk about the constraints on this. In the previous case, we looked at the relative components due to rates of change. So now, what's this? So we have a volume change that is not zero. So this is finite. We have a density change, which definitely is zero because there's no pressure change. And we have a sum of mass balances, which are these components here. And so we just need to figure out exactly what these are. In some respects, we make life somewhat easy for us, right? Because now if you look at this deforming volume, what's happening on this surface here? No fluid goes across here. It's the bottom of the beaker. It's not moving. This we're attaching to the top of the fluid, and so clearly the velocity across here, the relative velocity W2 has to be zero, right? Because it's moving with the thing. But the only one we have to account for is the one that we've already done, and that is W1, which is moving here. So in some respects, we've made it a bit easier, even though it's a deforming and kind of moving control volume, is that we've, bless you, is that we've made this, nothing goes across here, nothing goes across here, and so I think there's only one relative velocity we have to deal with. And so when we look at this expression, we have to figure how the volume changes with time, and we have to figure how on this one surface here, the flow rate occurs across here. There's no flow across here because by definition we've said that this is zero. So we don't have to deal with this, right? So there's only one active surface, and it's this. So we end up with this expression. The rate of change of volume, of the control volume, this has to be equal to the relative rate of flow into the system. The relative, sorry. How much does it change? How much does this volume change? Well, clearly this component here is going up and the volume is changing by this overall velocity V2 multiplied by this total area. So the top of the hockey puck is going up, and so the change in volume with time is the area of the hockey puck multiplied by its velocity. So that gives us this term here only. So we have that. So term A we have. Term B we have to figure out exactly what it is. So what is the relative velocity of the fluid across here? Well, this surface is going up at V1. Water is coming in, V2. So the relative velocity v1 has to equal the velocity of the water that comes across the surface. It's just coming into it. But the surface is also going up at v2. And so that means it adds to the velocity, right? Static surface, water comes across it at v1, it's coming in at v1. It keeps on coming in at v1, but the surface is moving up at v2, then it's just the sum of those two. And so the relative velocity is those. By definition, we said that mass rate in is negative, mass rate out is positive. So if this is net in, then this has to be negative. And so when we do this accommodation, this is our rate of change of volume with time. This is our density times the cross-sectional area, which is only this area here, A1, multiplied by the relative velocity W1. The water coming in at some rate, the surface going up at a different rate, the sum of those two. And this term here is negative because this flow is net into the system. So you can do it by looking at vectors, but I think it's easier just to get a feel for it. And so now if we have this expression, we can manipulate it to be able to figure out exactly what V2 is as a function of these. So we just separate this onto the left-hand side, so it's all in the same place. V2 is equal to A1 minus, this is just A2. And so if we just divide both sides through by A2, we get this expression here. This gives us the velocity. The time taken to fill is just the height of the beaker divided by the velocity at which the fluid is rising. Right? It has to go this high, starts at the bottom, it's going at this velocity. So the reciprocal of those two gives the time taken to fill. And not surprisingly, the time it takes to fill has to be exactly the same as all the other ones. So it's kind of artificial. We could have done the calculation quite easy just from the first one, but we've done three things. We've had a static control volume that hasn't changed in size, the hockey puck sitting at the bottom, stuff comes in, and the water flows out of the top of it. It doesn't move. We've taken a control volume that's a hockey puck that rises with the top surface, that moves up with the surface of the water. And we've taken a condition where the hockey puck expands and gets larger as we fill it up. Those are just examples of those three containers, if you like, the three different conditions we have. And not surprisingly, for each of them, we've got identical results in each case. And so we'll start off with this next time, but in dealing with these, all that we have to do is worry about the components. How fast the control surface is moving. Obvious if it's static and it's non-deforming, the control surface isn't moving at all, and the volume, since it's not moving or deforming, has to stay constant. In the case where it's moving but not deforming, then the hockey puck moves at some velocity, but its volume doesn't change with time. So this term has to be 0, but it's migrating with the top of the fluid. And the case where we have a deforming and moving case, then the control surface moves with the top of the fluid, depending on where you take your reference point, and the volume change of the control volume is not 0 because it's getting larger with time. And so that's how we deal with changing frames of reference. And so we'll leave it there for now. So have a look at this. It's not so easy to absorb, I don't think, but make note of the fact that we've solved exactly the same three problem in different ways. We should get exactly the same results for the time it takes to fill it after the bead of water hits the bottom, and that's exactly what we get by using this simple analog. And we'll leave it there, okay?